And finally, it's time to talk about more than one qubit. So we're gonna talk about 2 qubits and maybe even 3. We'll see. I'll try to keep it under 10 minutes as well. So the idea here is, and we're going to do the same from scratch in the sense that we're going to talk about the X, Y, Z, and those rotations first. And you will see, you basically see that at the end of the day, the logic the intuition that we try to build with 1 qubit is kind of the same with 2 qubits. But now you have 2 qubits, right? So if you apply an X gate to qubit 0, then basically out of all your space of possible values, and remember we have 2 qubits, so we have 4 possible combinations of values, then you're going to have your amplitude is going to be into the 0, 1. And here we care really about the entire system. Later on, we'll talk about the complexity of measuring just one of the qubits of a 2-qubit system, because that's not obvious. That's not like in a classical system where the full system is the sum of its parts. It's a bit different here. So, but for now, let's focus on this. So you can see 0, 1. If I apply the X gate here, then it's 1, 0, right? So I've applied 2 X gates and I have 1, 1. So that's the idea, right? So each qubit's amplitude goes from 0 to 1, and then you make up basically what you have is just one amplitude, so you have 100% probability of measuring 1, 1 right now. If you measure the circuit, then you have like 100% probability of seeing 1, 1. If I apply an X gate again here, we're back at 1, 0, right? Because we've negated these twice. So that's kind of what you would expect. And as I said, the same behavior happens with the other gates. If we're talking about the Y gate, then you have a 0, 1, but now this is basically this is a complex. That state has complex phase, because here remember that when we talked about just 1 qubit, even if we haven't done anything to the 0 qubit, what matters is that in total, that's what you have here. So if you apply 2 Y gates in here, now what you see is that you don't have a pink pink 1, 1, but you have a yellow 1, 1, and this is because you've got this this effect of the Y is kind of happening in both qubits. So they basically the phase of you have to think of the phase of the whole state is now changing. So it's the same as if you would apply twice the is it that's different. Why is it not? Anyway, so you see the effect is not obvious. So good. So if you do this way, you see it's like a pink one here. It's like exactly. And if we now go into and we turn that into an X, and we apply the Z1, then you're going to see that it turns basically yellow. So the logic is kind of the same one. I got a bit caught now by what happens with the Y gate twice. I definitely want to explore that a bit more, but I'm kind of realizing that it's, as you can see, it has like a funny effect where the basically the overall phase is affected by having that complex phase in each of the qubits. So that's an interesting effect. The Y gate is the one that's causing me the biggest trouble. So I definitely have to explore that a bit more. But that's the effect. And so if you now apply rotation gates, then it's the same concept, right? So if you rotate X, so now you see that you have a superposition of 0, 0, and 0, 1, right? Because you haven't done anything to the 0 qubit in here. So it's just that this is 0 or 1, and therefore your overall system is in a superposition of measuring. You can measure 0, 0, 0, 1 with 100% probabilities, but this guy has now a complex like a pink phase. And if I do here another one, then that's interesting. And what happens here, is you actually can see, that's pretty cool. I didn't think about it before as an illustrative way of how are those phases interacting with each other. So you can see that on, because here we've applied a rotation X with a pi divided by 2 parameter, right? And the thing is, when in this case you have two separate qubits, but you have to take a look. We're taking a look at the system as a whole. So, and you can see here in the different states how what's really happening with those two phases, that they actually interact with each other. And let me show you one first before I explain that, because let's remember what happened with when we're just at one qubit, right? Hola. Hello. Exactly. So what happened when we are just at one qubit and we use the Rx gate is that we are getting into a superposition of the zero stays with positive phase, and this stays with complex phase, right? So mathematically, this means that this is a complex number here, right? So if we now go back to 2 qubits, what is really happening here when we use this in our 2 qubits, right? Here we have the same effect as I just showed you with 1 qubit, just that we haven't done anything on the other qubit. If we do this here, we see that the zero state, right? Because the zero, when we apply the Rx gate in both qubits, the zero stays with positive amplitude, so positive phase. So the positive plus positive stays positive, right? In this case, if you remember, it adds. It basically adds a. So for each of the qubits, right? Remember that what it does to each of the qubits is it puts them into a superposition of 0 and 1, and for the 1, it makes it complex. It puts the phase into like the complex number. So what happens here is, because we've got 0 1 and 1 0, the 1 component stays complex and the 0 component stays positive, so that stays untouched, right? So it stays with this complex state. Now here we've got a 1 1 in this case, right? In this case, both ones, they would have a complex phase. But if you remember well, I said in the previous video that a sort of the complex in the circular, remember the phase is circular. So the complex phase is halfway through the negative phase. So in this case, both complex phases add up and they take you to the negative phase overall for the overall state. So that is really a good example of the weird interactions with 2 qubits. So you have 2 qubits that apparently they don't touch each other, but if you take a look at the overall system, you see those types of effects. So this makes quantum computing really powerful, but it also makes it extremely complicated to kind of tame and tweak to do the computations that we want to make. So the higher we go in our intuition sort of abstraction levels, the more complex it's going to be to know how to tweak certain things. But you here, this is a good example where it illustrates the phases of the 2 qubits interacting with each other. So when you take a look at the system overall, you have that effect. So at the end of the day, if we measure those 2 qubits, we're going to get, with 25% probabilities, one of those combinations. So pay attention, the phase doesn't affect at all the probabilities of measuring something. But it gives us an extra dimension of calculation of computational space. So we can actually compute with phases. We can play with stuff. You can see that they add up, right? So as soon as they are implicitly adding up, so as soon as you realize that, you can try to control this and say, okay, so if 2 complex phases make up for a negative one, you can start thinking about different ways to make arithmetic in here. So, and then you can think about how can you make phase arithmetic. So how can you add the phases, subtract phases, do weird things like that. I mean, weird, fancy things like that. Yeah, and at the same time, you can also think of how do you make arithmetic in the amplitude realm, right? So here we've got a superposition of all possible values, but what if we do this? So what if we, so there you had an example. So what if we, or maybe a simple one, let's say that we do a Hadamard in here, right? So so now we have a superposition of 0 0 and 0 1, right? But our computational space, like the system allows us to represent 4 different states. So is it possible for us to, like, I don't know, say add +1 to all of this, say 0 0 plus 1 and 0 1 plus 1 at the same time, so they both turn into like So the 0, 0 would become 0, 1, and the 0, 1 would become 1, 0, right? Because 0 plus 1 is 1 and 1 plus 1 is 2. Is it possible to do that? Yes, it is possible. And that's kind of called that's I think in some of the places that I've been using to learn, they call that amplitude arithmetic. So you're operating in using your amplitudes, and you're doing arithmetic, and you're doing computation with your amplitudes, versus doing computations on the phases, which is sort of a different concept. But you see, this is just a beast in terms of the bunch of things that you can do. How you're going to do this arithmetic, we'll explore later on in another video. But I mean, I don't even know myself. I don't even remember. I don't have it on top of my head. But I think if you, I think if you basically, it's something with a not with the X or control X. I don't know. We'll explore this later. But you can basically move those things around, and I don't know. Just let me play a little bit with it. Okay, so here you've now moved the amplitudes to this side of your space. Yeah, anyway, we'll explore this later on in another video. But basically, this gives you an idea. So you basically, when you add qubits, you kind of create a space. You create two computational spaces: the amplitude space and the phase space. So, and you can operate in both worlds, and you can have computations that done in the phase side don't affect your measurement, so don't affect the probabilities of seeing a certain state. So you can, it's kind of like if you'd have, I always think of this as like you can do computations sort of on another dimension, and then even there are probably ways you can flip things and switch information from your phase to your amplitudes and vice versa, so you can kind of then read your results. But that's a rough idea of the power that this creates when you add qubits. What if you add 3 qubits, say, or 4 qubits, right? So now your space grows. So now with 3 qubits, you can represent up to eight possible states. So now you can do much more with this, right? So you can go into full superposition here, and things like that. You can apply the you can do what we were doing before. You can add, like, so for example, this is a good example, right? So the rotations with z's. So what happens, you can see what happens if you apply it to each of the qubits. You see that it's actually not affecting your amplitudes, as I said, but it's affecting your phases, and it's affecting the phase of every single state that has a 1 as its lowest qubit, right? So 1, 1, 1, and 1. Whereas if you apply it here, it's doing so for those states where you have a 1 in the second qubit, so to say, and here it's in the third qubit. So you see that it kind of, you're painting different patterns that you can then use to compute stuff. It's all about then mapping that to whatever data structure or system that you want to work with, and then make computations with this. So sure, it's complicated, but that gives you an idea of the power of this beast, right? And then potentially you can do operations that you usually would have to do for each of those elements, but you can do them once for all the elements, and that's where most of the speed ups in different algorithms come from. Yeah, so that's basically showing you a bit of the power of working with multiple qubits more in detail.